Okay, so if we want to understand the equation of a line or a plane, it's really important that we first understand the idea of a position vector. It's a really simple idea, but let's make sure we really understand it. So let's just start in 2 dimensions. Let's say we have a point sitting out here, and let's say that's the point, I don't know, 7, 3. Now this, of course, is just a point, and it has the coordinates x is 7, y is 3. And what we can do here is we can take a vector, start it at the origin, and just have it, the head of that vector point right at 7, 3, at that point. And so this vector, now it moves over 7 in x and it moves up 3 in y. So that is the vector. Let me call this r0. We'll see why I'm calling that later on in the video. But now the vector r0, it has the components. The x component is 7 and the y component is 3. And this is what we call the position vector of the point 7, 3. Okay, so the difference between the two, the difference between the point and the vector is one is a point and one is a vector, but they tell us essentially the same information, because if we know the point, of course, we can easily write down the vector. It's just the same numbers. And vice versa, if we have the vector, then if we start that vector at the origin, it will point right at the point with the same numbers. Okay, so this is what we'll often kind of switch back and forth between knowing a point and knowing a position vector. We'll use them basically interchangeably. And the only difference is a point is a single point, whereas a vector, of course, is the entire arrow. But they tell us essentially the same information. Okay, so that's the starting point. Make sure you understand that. Now, let's say we have a line here floating out in space. The key information to knowing this line is we need to know a point on the line. Or let me do this with numbers here. The first thing we need to know is a point on the line. And we also need to know a direction vector. So we kind of need to know what direction is the line going in, and the way that we get that information is with a direction vector. So here's a point on the line, and let me draw a direction vector in a different color. This is a direction vector, and I'll call that direction vector the vector D for direction. So now that we know a point on the line and a direction vector, well, having that point is really the same thing as having a position vector. So that right there is our position vector r0. It starts at the origin, and the head is at that point. So the tip of the vector is right at that point that we know on the line. Okay, so now what do we need to do in order to get the equation of the line? Well, what we're first gonna do is get the vector equation. And so let me just kind of split this off. The vector equation is this. Maybe first what I should do is just tell it to you and then explain why it makes sense. The vector equation is that any position vector on the line, so any r, can be written as first r0 plus a scalar, which I'll use the letter t because that's supposed to be like time, times a direction vector. And why does this make sense? Well, if you think about what addition does, addition in terms of vectors is actually just head to tail addition, right? So if we can think of the equation as telling us this. First use our position vector to march up to this point on the line. So now we're here. And then we use our direction vector to move along the line. So this is exactly head to tail addition. So R naught plus D, just R naught plus D, so plus 1 times D, for instance, will give us this vector right here. It'll point right to that point on the line. So that is R naught plus D. Because it's just head to tail addition. First here, then there. And the vector you get starts at the starting point and ends at the ending point. Or what about R naught plus 1/2 D? Well, 1/2 D is right here, right? That's half of D. So we first march up R naught to get to this point on the line, and then we march over half of D, and we get this point on the line. So what we're getting is we're not actually getting the point on the line, but we're getting this vector in blue. R naught plus 1/2 D. But like I said, knowing a position vector, so R naught plus 1/2 D is the position vector of this point. So if we know all the position vectors of the line, then we know all the points on the line. So this is a vector equation. So this is called the vector equation of the line. And what it tells us is all the position vectors. But like we just talked about just now and in the first part of the video, knowing all of the position vectors is the exact same thing as knowing all of the vectors. Or sorry, as knowing all of the points. Okay. And you know, we can just so now what we can do is just, we already did 2 examples. We did when t is 1 and when t is 1/2, and we saw we got 2 different points on the line. But you can imagine if you let t just vary, so if you let it be any number you want, all we're doing when we do that is we scale d. Like if we let t be really big, we first march up R naught, we land at this point, and then we march really far along d and we get a point on the line way out here. Or we take a negative t and that flips the direction of d and we multiply by some number and maybe we get a point out here. So, and in fact what we really get is we get the position vector. We march along R naught up to the line and then we march in the direction of d however far t tells us to go. Okay, so hopefully conceptually that makes a lot of sense where this vector equation is coming from. Let's do an example to really make it concrete. So let me just rewrite that vector equation so we have it handy. To get any vector we want, we can write this as R naught plus TD. So again, I'm going to emphasize this. What information do we need? We need a point. But knowing a point is the same thing. It's good enough to know a position vector. So either know a point or we know a position vector. But either way, what we're going to use is this R naught. If we're given a point, we'll just convert it to the position vector and call it R naught. And we need a direction vector, which I've been calling D for direction. And once we have those 2 pieces of information, we just plug them in to this formula. We plug in for R naught and we plug in for D. So, example. Let's find the equation of the line, the vector equation of the line, passing through the point 1, minus 1, 4, and in the direction of the vector 3, 5, minus 2. Okay, so what do? We just use this is a relatively easy example because they told us a point that we're passing through. So we know a point, and they told us a direction. And in fact, they gave us a direction vector. It's in the direction of this vector. So this is our point, or underlined in orange, and this is our direction vector underlined in yellow. So what is the equation then? What does that become? It's our vector equation is r is equal to, well, r naught is the position vector of this point. So we just convert that to a vector, 1, minus 1, 4, plus a scalar times our direction vector, which is 3, 5, minus 2. And again, the reason we use t for time is a lot of times when we're thinking about curves in 3 dimensions, we think of them as like a particle moving around in 3 dimensions. And so t is supposed to represent time passing as that particle moves around. Okay, and so this is the vector equation of the line. Let's take it a little bit further, simplify, and talk about its parametric equation. So if we just do vector, or first, let me do this in a bunch of steps because it's our first example. First thing is we can take this scalar, this real number t, our variable, and multiply it in. And what do we get? We get t times 3, so 3t, and t times 5, so 5t, and t times 2, so minus 2t. And then we can add these together. So vector addition, you just do component-wise. So 1 plus 3t in the x component, minus 1 plus 5t in the y component, and 4 minus 2t in the z component. Okay, so this is the final answer. This is the equation of the line, the vector equation of the line. And what it's telling us is, given any number t, you can plug that in, and it will tell you a position vector of a point on the line. And the position vector will have the x coordinate here, the y coordinate this number, and the z coordinate this number. And so we can convert this to a different form of the line, where we just say every point on the line, the x component is given by this, the x coordinate of our position vector, or the x component of our position vector, and the y value of the point will be the y component of the position vector, and the z value of the point will be the z value of the position vector. So if you know the vector equation, like we know here, we can very easily convert that to the parametric equations, because we just take out the x component and write a little x equals this x component. And then we take out the y and we write y equals the y component, and then we take out the z and we write z equals the z component. So it's a very simple conversion. So if you're given parametric equations, you could easily convert to the vector equation by just throwing these into a vector. Throwing these expressions with t here into the vector. And vice versa. If you have the vector, you can just pull it out and write, oh, well, x equals the first one, y equals the second, and z equals the third. Okay, so this was a simple example, but I hope it illustrates the concept. See you in the next video.